Hello everybody, today we're going to look at some examples on how to use the normal distribution. So our first example is a non-calculated question, and in this question we're kind of given the regular normal distribution percentages, and we can use these to help us work out some scores. So the chest measurements of 18-year-old male footballers are normally distributed with a mean of 95 centimetres and a standard deviation of 8 centimetres. So straight away from there, we can draw a picture. So let's do it directly underneath that nice example we've got. So we are centered around a mean of 95 centimeters. And we know that we've got a standard deviation of 8 centimeters. So if we think about this, well, that means at 103, and we're going to go as low as 87, we're going to be within one standard deviation away from the mean. And if we move that across and add another 8 to the 103, we will have 111. And if we go down 8 from our 87 to 79, we can say that we're within two standard deviations of the mean between 79 and 111. Okay, so now we can answer these questions. So A, find the percentage of footballers with a chest measurement between 87 and 103. Well, on our picture, we're looking at all of this, aren't we? That's going to be what it is. And if it's normally distributed, we can use our values there, look, to work it out. So our answer for this one is going to be as a percentage, 68.26%. As a decimal, will be at 0.683. Okay. Next one is the probability of being between 103 and 111. So in our diagram, we're looking at this particular area here, but we can see clearly already that's going to be a probability of 13.59%. So if I was writing that as a decimal, perhaps, it would be 0.136. Part B. Find the probability that the chest measurement of a randomly chosen footballer is between 87 centimetres and 111 centimetres. So in this one, we're looking at the combined probability of us being in this area I'm shading in right now. Well, we can do that again compared to that previous diagram because we have those numbers. And so we're going to add the 34%, the 34%, and the 13.6% together, and that's going to give us our answer. So for this one, if we do that as a decimal, we'll be at 0.819. C. Find the value of K such that approximately 16% of chest measurements are below K. Well, if we think about this in terms of our first diagram, we're looking for combined probabilities of 16%. And it's going to be on this left-hand side here. If we take the 13.59, the 2.15, and the 0.13 for those little bound areas there, we're going to get approximately 16%. So the question is, well, what was this value here? That would be our value of K, so that 16% of chest measurements are below K. And of course, if we follow that down to our diagram, match that up, that is going to be 87 centimeters. Okay, on to example 2. Now, example 2 is where we're going to leave the context and we're going to look at this really, okay, with a calculator and just plugging things in and making sure we understand what's going on. So first of all, let's understand the notation here. X is a discrete random variable, and it's telling us in this piece of notation that it is a normally distributed discrete random variable. Sorry, random variable, I should say. Now, the 10 refers to the mean, right? We've got a mean of 10. And when we say 2.3 squared, we're saying that the standard deviation is 2.3. It is notation that that gives us a squared, and you will always see the squared there. It's referring to the variance. So we know that mean is 10. We know that the standard deviation is 2.3. So we need to work out a probability that we are between 8 and 11. Now, for every one of these questions, you need to draw a diagram so we check that our answers make sense, we haven't made a mistake. So every single time, try to do this. So we know we're centered around 10. And that means that when we have our 8 and our 11, what we're doing is we're looking for this area here. Okay, let's just carry on and do B and C in this diagrammatic form first before looking at how to use the calculator. For part B, if we're drawing this, again, we are centered around 10, but we're looking for that place where we are less than 12. So 12 is going to be to the right of 10, and we actually need to work out on our calculators what this area here is going to be. And finally, the last one, again, we are centered around 10 because we've got a mean of 10, and we're looking for the probability that we are greater than 9. And so it's going to look like this. Now, when we're normally distributed, we're really looking at sort of a continuous variable. Okay, we're adding things up. So do not pay too much attention to whether we're including the 11 or not. It's so insignificantly small that we don't really need to worry about that. Just think about the numbers. Okay, so now it's time for the calculator, and there is a button on your calculator that's going to help us to do that. So if you press the distribution button, and then you'll see a menu. The button we need every single time is normal CDF. That's the button. So see if you can find that on your calculators. Now, when you are faced with that screen, you're asked to input some things. So let's have a look at what that means. So we're going to go back to example A now and have a think about this. Well, we already know the mean, and we already know the standard deviation. That's going to be the same for all of these questions. The mean is 10, the standard deviation is 2.3. But in this question here, we're asked for the boundaries, and we are asked for a lower boundary, which of course is going to be 8, and an upper boundary, which is going to be 11. So if we input those values in on this screen here, press enter, we're going to be left with an answer. So our answer for this question is a probability of 0.476 rounded to 3 significant figures. Okay, on to B. Let's have a look at what we've got to do for B again. So in part B, we're looking for the probability that we're less than 12. Well, clearly, the upper boundary is 12, right? Okay, but the lower boundary goes on infinitely, all right? This goes on forever. So what I want you to do is put negative 99999, as many nines as you can, into your calculator, and that is going to be accurate enough for us. So there's how we do our lower boundary. Here's our upper boundary. We've got the same mean and standard deviation as usual. So if we press our button, we should end up with our answer 0.808 rounded to 3 significant figures. And look, this goes on forever. That's why we have this negative 99999. So of course, in the final part of this, see, we need to know what the probability is when we're greater than 9. So clearly in this one, our upper boundary will be positive 9999999 forever. And our lower boundary here is going to be 9, right? That's how we're going to work this out. So exactly the same, normal CDF, lower boundary 9, upper boundary 9999999. We've got mean of 10, standard deviation 2.3, press the buttons, and we are left with this answer. Check that you can get the same answers as me. This one is 0.668. Okay, we better do a question in some context now. So let's have a little look at this one. So in 1972, the height of rugby players were approximately normally distributed with a mean of 179 and a standard deviation of 7. Find the probability that a randomly selected player in 1972 was, and we've got some questions here. So straight away, let's write down some key information. We have the mean is 179. We have that the standard deviation is 7. And so let's just be really specific about this and practice our notation. In terms of what we will see on an exam paper, perhaps, it would be 179 as your mean, and we'd have a 7 squared there. Okay, so we are trying to find in part A at least 175 centimeters tall. Well, this implies that our variable x is going to be greater than or equal to 175. So let's draw a little picture. I won't go through the calculator work every single time, but if we've got 179 in the middle, the reason we draw this is because we should be expecting an answer that is greater than 0.5. Because we have this mean given to us, clearly you can see from the diagram that we are over half the area. And this curve has an area of 1. So if we are going to work this out on our calculator, we should be getting an answer greater than 0.5 for this one. So we'll do the normal CDF. Lower boundary is 175. Upper boundary is 999999999. We've got our mean and standard deviation of 179 and 7. So we press the buttons and we end up with 0.716, which is correct. B. This time we need to know between 170 and 190. So if we have our middle of 179, we're going to have something like this occurring. We're looking for this area there. So again, we type it in normal CDF and we should get out an answer of 0.843. Check and see if that's what you get as well. Okay, final example now. Example 4. So this one is a little trickier. The time taken by students to complete a puzzle is normally distributed, and we have a mean of 28.3 and a standard deviation of 3.6. Okay, calculate the probability that a randomly selected student took at least 30 minutes to complete the puzzle. So that's more than 30 minutes. So what we're looking for in part A here is the probability that we are greater than 30. So if I was drawing this out again on a little table, well, I would have my 28.3 in the middle. So this time when I press the buttons, I should be expecting an outcome that is less than 0.5. Okay, so we've got our mean standard deviation, we've got our lower boundary, which is 30, our upper boundary is 9999999. We press the normal CDF button and type it all in, and we get an answer of 0.318. Okay, part B. Out of 10 randomly selected students, at most half of them took at least 30 minutes to complete the puzzle. This is a headache, this one. This is very challenging. The answer to this is it is absolutely not anything to do with the normal distribution. We have to be really careful here. Yes, it is normally distributed, but now we've thrown in something else into the mix. We've got 10 students. And of course, they can either do it in 30 minutes or not do it. So when there's those two choices of outcome, success and failure, we need to be remembering our work on the binomial distribution. So if we called this random variable y, we would say that, well, y is a binomial distribution where we've got n, the number of things, is 10, okay? And the probability of the success, well, we worked that out in part A. The probability of this happening and being greater than 30 minutes is 0.318. And I think that was actually 38 if we round that a little bit further, because we'll need to be as accurate as possible when we do this. So we want at most half of them. Okay, so that means that in terms of what we type in on our calculator, we want our new variable y to be less than or equal to 5 at most half an hour. At most half of them. That's 5 of them. So we can just type that in. We have 10 trials, binom CDF, of course. 10 trials. We've got our probability. Our x value is 5. We press the buttons, press enter, we're going to end up with our answer of 0.938. So just be aware, you could be asked about binomial as well as normal, and you need to know when to use each of the two different things. Okay, so following on from this, you should be able to do 24A, which requires no calculator, just that table to help you look up probabilities, and then 24B, which is some practice using the calculator for normal distribution problems. Good luck with the work.